In this video, we're going to go over a few more examples of the basics of incompressible flow using the continuity equation and the momentum equation. This is going to be the basic layout of our examples. It is going to be a simple wind tunnel, and we're going to have sensors on the bottom and the top walls to measure the pressure there, and we're going to have sensors along the y-axis of the inlet and the outlet to measure the velocity of the flow at different y points along the outlet. The purpose of the examples that we're going to be doing in this video is to determine the drag on an airfoil without using a pressure sensor on the airfoil itself. We're going to determine the drag on the airfoil using the sensors for pressure and for velocity along the walls and the control surfaces. Here's our first example. You will need to calculate the drag force and the viscous force on the airfoil. We will be assuming that the pressure is constant along the walls and at the inlet and the outlet. Also note that the density is in kilograms per meter squared because this is a two-dimensional problem. Using the momentum equation, we see that the pressure components cancel each other out because the normals are opposite to each other and the pressures are equal. That leaves only the density and the velocity components of the momentum equation, which we can solve by taking the very simple integrals and then solve algebraically to get the drag force of 23,000 newtons. To think of this visually, the viscous force is a force on the fluid, and that is a force that is on the entire fluid, where the drag force is a force on the airfoil itself, and these forces must be equal and opposite. Here's our second example, and this example will be much more accurate to real life. We will be assuming that this is a symmetrical airfoil and it will be at zero angle of attack. This will mean that the pressure on the bottom and at the top of the airfoil will be the same. And with this assumption, the pressure on the walls at P3 and P4 will also be equal. I calculated the pressure at the outlet using the Bernoulli equation after taking the average velocity and using that to calculate the outlet pressure. Using the momentum equation to solve for the viscous force, we see that the two pressure components from the walls cancel each other out again, but the pressure components at the inlet and the outlet do not. Note that the viscous force and the drag force decreases by more than half now that we take into account that there is a pressure differential behind the wing. Looking at this visually, it makes sense because we have a higher pressure behind the airfoil and a lower pressure before the airfoil, which is going to give us a net pressure forward, pushing the airfoil into the flow, which is going to decrease the drag force on the airfoil itself.